So last time we learned how to divide a polynomial by another polynomial using a process called polynomial long division. And to use this as a reference for our lesson today, I want to do this process one more time, but since we already have a video covering the details, I will go through this a little bit faster than usual. So x goes into here, 2x cubed times all of this gets me 2x fourth minus 6x cubed. Subtraction gets me x cubed. Bring down the negative 8x squared. Then x goes into this, x squared times these terms give me these terms. Then subtraction gives me negative 5x squared. Bring down the 2x. X goes into there, negative 5x times. Negative 5x times all of these gives me negative 5x squared plus 15x. Then subtract gives me negative 13x. Bring down the 4. X goes into there, negative 13 times, and negative 13 times the entire divisor, negative 13x plus 39. The final subtraction gives me negative 35. Okay, so we would have taken this expression and written it as the quotient, which I'm going to read off the top here, 2x cubed plus x squared minus 5x minus 13. And then the remainder, negative 35, we placed over here over the divisor x minus 3. Okay, this part, the quotient, and this part, the remainder. So today, we're going to investigate another way of writing this for a very specific case, where the denominator is a linear polynomial, so it's going to be 1x plus or minus a constant. In those cases, we are able to use an algorithm called synthetic division. Step 1. We take the coefficients on the terms in the numerator and we list them out. We'll start with the 2 from the 2x to the fourth, then we go negative 5, then negative 8, then 2, then 4. And then we will place a box to hold the information from the divisor. So it's always x minus some number. This number right here is going to go in a box in the upper left corner. And then we draw a horizontal line. Procedurally, the first step now is to bring the leading coefficient down, never touch it. And then we'll do a sequence of diagonal down by saying every time we go diagonal, this number gets multiplied by what's in the box, which becomes 6. Then every time you go down, you will add the numbers vertically to get 1. Diagonal means multiply by the number in the box. Down means add these together. Diagonal means multiply by the number in the box. Down means add. Then diagonal means multiply by the number in the box. And then down means add. And this number, I'm going to box because it has a different significance than the rest. So, what we're seeing here is because this has a coefficient of 1 on the x term, if I were to do long division, then my leading coefficient in the quotient would always match my leading coefficient in the dividend. This is an always thing. So by bringing down this 2, that 2 is representing the leading coefficient in the quotient. In long division, I would then take this 2 times negative 3 to generate negative 6. But in synthetic division, I flipped the sign to make positive 3 instead of x minus 3. So by taking 2 times 3, I get 6, which is the opposite sign of this negative 6. And in long division, I'm subtracting, but since I flipped the sign, in synthetic division, I'm going to add. That gets me a 1. And that 1 represents this 1 here, which is going to match the 1 in the coefficient of this next term, because the coefficient on this x is 1. So, here in long division, 1 times negative 3 gives me this negative 3. But since I flip the sign in synthetic division, I get the opposite. I get positive 3 here. But then when I add them, this negative 5 will match this negative 5. hence matching the negative 5 coefficient in the next quotient term. Negative 5 times negative 3 gets positive 15, which, flipping the sign, gives me negative 15. Adding together gets negative 13, which matches this negative 13, and therefore this negative 13 up there. Negative 13 times negative 3, positive 39, but the flipped sign over here gives negative 39, and finally that negative 35 is the remainder. So in a normal pre-calc class, you probably won't need to know how all of the numbers relate to the numbers back here. But what you will need to know is how to generate the top row using the coefficients on the numerator terms, how to get the number in this box, because it's x minus that number, and then that this at the end represents the remainder, that negative 35 is down here, and therefore up there, and that these numbers represent the coefficients on the quotient terms. So the 2, 1, negative 5, and negative 13 match with those. Next to the remainder is always the constant term. And then increasing in powers of x, you go x squared, x cubed, and if you had more terms in the problem, you would go x fourth, x fifth, and so on. And hopefully you can appreciate that this method is a lot less writing, which makes it a lot faster and a lot more convenient. But remember, the restriction is the divisor must be linear with a 1 coefficient on the x. And if that's not the case, you need to manipulate your problem to establish this first before you can go and do synthetic division. Let's do an example where we have some skipped terms. So in the numerator, we'll have 4x to the 5th minus 19x cubed, skipping the x to the 4th term. And then we'll have skip the x term and have a plus 5. Then we'll divide by x minus 2. So the divisor is linear with a coefficient of 1 on the x. So those are the conditions met to use synthetic division. Coefficient, first one is 4. Then there's no x fourth, so I have to put a 0, or else I'll have a bad time. Then negative 19. Then positive 3. Then nothing here. And then finally the 5. So in the box, it's x minus 2. So this number right here goes right there. 4 comes straight down. Then to go diagonal, I'll multiply by 2. Then I'll come down, add. Then 8 times 2 to go diagonal. Then I'll add. Negative 3 times 2 to go diagonal. Then I'll add. Negative 3 times 2 to go diagonal. Then I'll add. Negative 6 times 2 to go diagonal. And my final addition gives me the remainder. So this set of numbers gives me the coefficients on the quotient in the order of constant right next to the remainder, then up x, x squared, x cubed, and x fourth. So when I take this expression, I will rewrite it as 4x to the 4th. Next term, 8x cubed. Next term, negative 3x squared. Next term, negative 3x. And then negative 6 is a constant. And then finally, the remainder of negative 7 will go up here over x minus 2. And there we have it. Let's now do an example where the denominator is an x plus a number. So the conditions to use synthetic division: divisor is linear, the coefficient on x is 1, so we can do it. We'll pull the coefficients off the numerator terms, so that's 3, 12, negative 5, and 2, no skipped terms. In the box, we can rewrite this as x minus negative 4. So negative 4 is what goes in the box. And you can think of this as, switch the sign, you can think of it as the number that makes the denominator 0, or you can think about it as x minus the number, which is probably the most technical way of thinking about it. 3 comes straight down. 3 times negative 4 to go diagonal. Add them to go down. 0 times negative 4 to go diagonal. Add them down. Negative 5 times negative 4 to go diagonal. Add them down to get the remainder of positive 22. So we would rewrite this expression using the quotient. Counting constant x, x squared gets me 3x squared plus 0x, so I won't bother writing it, and then minus 5. Then we have a remainder of 22, so we go plus 22 over x plus 4. So remember, if the denominator is x plus something, flip that and make this a negative number in there. It's always x minus whatever the number you have. Let's do another example. We'll go x cubed plus 5x squared plus 4x minus 6. We'll divide this by x plus 1 minus root 3. Now, that denominator is just root, but the coefficient of x is 1, and it's x plus a number, so we've met the conditions to do synthetic division. Numerator coefficients, 1, 5, 4, negative 6. 1, 5, 4, negative 6. No skip terms. And in the box, I can rewrite this as x minus that. It's just the opposite of this. And so this number is what's going to go in the box here. The 1 comes right down. 1 times this is just itself. And then when I add, I'm going to take those and combine like terms. I'll get 4 plus root 3. Then I have to take this number and multiply by that number to get here. So I'll go ahead and write this off to the side. 4 plus root 3 times negative 1 plus root 3. This gives me 4 times negative 1 is negative 4. 4 times root 3 is 4 root 3. And then root 3 times negative 1 is negative root 3. And then root 3 times root 3 is just 3 at the end. So this should get me negative 1 combined, and these two get me plus 3 root 3. So as a result, this times this will get me negative 1 plus 3 root 3. And when I add these together, 4 and negative 1 are like terms. I get 3 plus 3 root 3. And now I have to take this times that. So I'll write that over here. 3 plus 3 root 3 times negative 1 plus root 3. 3 times negative 1 is negative 3. 3 times root 3 is plus 3 root 3. Then 3 root 3 times negative 1. Good news, these will cancel. And then finally, 3 root 3 times root 3 is 3 times another 3, which is 9. Then these are gone. Negative 3 plus 9 is 6. So we get a nice 6, and even luckier, we have a 0 remainder. So we could write this expression as, in the quotient, that's constant x and x squared. So this is 1x squared plus 4 plus square root of 3x, and then this is the constant plus 3 plus 3 root 3. And there's no remainder, so there's no last term. But remember, this means that technically we have to add the condition that x cannot equal the number that would make the denominator 0, which means x cannot equal this negative 1 plus root 3. There we have it. It's worth asking what happens if the coefficient on the x in the denominator is not 1. So let's try one. And we see that is not 1, which I earlier said meant that we need to manipulate this problem to make the coefficient 1 right there. So what we're going to do is we're going to factor the 3 out, which will give us 3 times x minus 2/3. And when you factor a 3 out of the denominator, I can pull it out and rewrite my fraction like this. The numerator will stay the same. But the denominator, I factored the 3 out, so I will simply have x minus 2/3 over here. So that is something we can use synthetic division on. We're going to leave off that 1/3 for now, and we're going to come back to it later at the end. So the coefficients on the numerator, negative 12, 11, negative 6, 5, and negative 1. And in the box, this is going to be x minus 2/3, so we put the 2/3 in the box. Fractions are okay. We've already done more obnoxious numbers, right? So negative 12 will come down directly, which perhaps answers the question, can the leading coefficient be negative? Totally. Negative 12 times 2/3 gets me negative 8. Add them down gets me 3. 3 times 2/3 is 2. Add them down is negative 4. Negative 4 times 2/3 is negative 8/3. And then I can add numbers. Common denominator makes 15 over 3. So add them together, I get 7 over 3. 7 over 3 times 2 over 3 is 14 over 9. Then common denominator, negative 9 over 9 plus that gets me 5 over 9. We can do fractions. So the quotient, constant x, x squared, x cubed, and the remainder. But when I write this very carefully, I will retain the 1/3 out front. And inside here, I'll write the quotient and remainder. So we'll go negative 12 x cubed plus 3x squared minus 4x plus 7/3, taking these for the quotient, and this 5/9, I'll say plus 5/9 in the numerator, divided by x minus 2/3 for the denominator. And the last step is going to be taking this 1/3 and distributing it through all of these terms. So 1/3 times negative 12 is negative 4. 1/3 times 3x squared is x squared. 1/3 times negative 4x gets me negative 4/3 x. 1/3 times 7/3 gets me 7/9. Now, when I approach this last term, what I'm going to do is I'm going to take this 3 and multiply it to the denominator, and take the 1 and multiply it to the numerator. That gets me 5/9 on the top over 3x minus 2. And the reason for doing that is now this divisor matches the initial divisor we had. And so sometimes we will take this 5/9 and write the 5 on the numerator, the 9 on the denominator. I like this form because it makes it more clear what the remainder is. But this right here, notice that those coefficients don't match these coefficients. They result from taking the coefficients divided by the number that you factored out of the x term at the beginning. I find that the last question type we did is really where I get the most questions from students. So why don't I do another one just so we have some more variety? We'll go 6x cubed plus 7x squared plus 24x minus 3, and let's divide this by 4x plus 10. Once again, the coefficient on the x is not 1. So what we did before is we factored out this 4, and that will get me x plus 5 halves, also known as x minus negative 5 halves, right? Okay. The initial step was to take that 4 and factor it out of the denominator, which puts it in the position right here in the denominator. I'll put it in the brackets. The numerator stays the same, 6x cubed plus 7x squared plus 24x minus 3 divided by, and now I have x plus 5 halves on the denominator with that 4 sitting out front. So it's time to do synthetic division on just the part in the brackets. So numerator coefficients, 6, 7, 24, negative 3. And in the box, I have the negative version of this, so negative 5 halves. The 6 comes straight down, multiply by negative 5 over 2 gets me negative 15. Add it down gets me negative 8. Negative 8 times this gets me positive 20, and then bring it down, I will get 44. Then 44 times negative 5 halves, a little bit obnoxious, is negative 110, and then add these down is negative 113. So I'm going to very carefully retain the 1/4 we factored out, and then produce constant x, x squared. So we'll have 6x squared minus 8x plus 44, and then the remainder of negative 113 all over x plus 5 halves. And the final step will be to take this 1/4 and distribute it to all the terms, which will get me 3 halves x squared, then minus 2x, then plus 11, and then, like I did last time, I'll multiply 1 to the numerator and 4 to the denominator, which will get me, on the bottom, 4x plus 10, and now the denominator matches my original divisor. And this is the answer. So once again, if you see the pattern, what you're going to do is take this and factor out of 4 to decide what goes in the box. Then once you're done, you'll take the quotient and divide each term by the number you factored out of the denominator. So I'm dividing each of these terms by 4, same thing as multiplying by 1 over 4. But the remainder is going to stay the same. I would like to end today on this example, which is a little bit different in style from the ones we've been doing, but it's a very standard example, and you'll find it in a lot of different textbooks. So we see this letter C, and the problem statement will come with something like, find the value of C such that the remainder is, and it will state some condition on the remainder. So perhaps I'll say the remainder is 0, because this statement now is equivalent to saying, find the value of C such that the denominator divides evenly into the numerator. But this number could be whatever the problem says it is. And in order to deal with this, we're going to perform synthetic division, 3, then no coefficient for the x cubed, then negative 5, and then the coefficient for the x is just c, so I'll put that there. And then in the box, this is going to be x minus negative 2, so I'll put a negative 2. Then we will pull the 3 down, 3 times negative 2, then add them together. Negative 6 times negative 2, we'll add them together. Then 7 times negative 2. And when I try to add these, c is still an unknown value, so I have to write it like that. And then this times negative 2, distributing yields that. And then when I add down, I should get negative 2c plus 24. Now at this stage, this is my remainder. And I go back to the problem where it tells me that my remainder is 0. So I will say negative 2c plus 24 is equal to 0, which then, moving the 2c over to the other side, yields this. So c is equal to 12. And evidently, this is the value of c that satisfies the given condition. And you can get really creative with things like this. You can put c's other places. You can have expressions involving multiple letters, and then you would have to have multiple given constraints. But at the end of the day, a constraint placed on the remainder just prompts you to perform synthetic division to get an expression for the remainder, and then perform algebra to satisfy whatever condition was given. Well, thank you for listening, guys. I will see you next time.